wasn't streaming. Experienced a hiccup. Well, at least it is now. Now Milan can attend. Yeah, I know, but now he can still attend if he wanted to. Sorry, what? Well, then if he comes back, he could reverse that score. Thank you. Now, if the reaction is going along well, these bonds are forming, the old bonds are weakening, then in that particular case, excellent, thank you. Grab your notes, pull them out. We're making stuff. Taylor? What are you doing? Okay, do you want to go get some Tylenol or something from the health center? What we end up having here then, we've got new bonds forming. We've got our product. You're still turned forward. Not, yeah, but loudly, spontaneously, and not about chemistry.
It was not. It was about chemistry.
About this chemistry we're doing right now?
Yeah.
No.
That's what we were talking.
Nope, I'm just denying that right out. Hydroiodic acid. And of course these are called products. Does everybody have the entire diagram down? Does anybody not have the entire diagram down?
I don't have any.
I just had a question about.
Yep.
Conservation of energy.
Yeah.
What are the variables in potential energy?
So the potential energy and the kinetic energy must always add up to the total energy.
Yeah.
Now that gets more complicated because you can divide kinetic energy into like sound, vibration, and you have to account for all the bits, and then of course light can be given off, so then you have to account for that separately. The energy at the beginning and the end should always be the same. The law of conservation of energy and the law of conservation of mass turn out to be the same thing, because sometimes you don't have it obeyed, but that's nuclear chemistry. Tiny bit of mass disappeared and it got turned into energy, equals mc squared, but the overall amount of energy you got out equals the amount of mass that disappeared.
What is the variables that you put in numbers in potential energy?
Oh, just the energy in joules. Like you'd calculate the potential energy it has at the beginning and the end.
Isn't there can't you input a certain distance?
Oh, for potential, yeah, gravitation times height or something, yeah. But that's easy physics stuff. I don't do that. Dylan, you're just gonna have to catch up, get the notes off someone else as you do so.
What's the difference between the law and the theory?
Law is just a summary. It's nothing special.
The law is proven.
Nothing in science is proven. Who said law is proven?
Nick, what was your question?
Oh, nothing in science is proven.
Wait, so then...
So science is made up?
No, no.
all
Is Darth Vader Luke's father? Yes.
Oh, no. That's what they told us.
The reason that's true is because we made it up, and an author actually said it was true. Do you capitalize the beginning of your English sentence? Yeah, that's 100% true, because whoever came up with the rules of English, we just made it up, and you could change it tomorrow. The only things that are 100% true are the things you invent. Stuff in science, like math, is proved because we made it up. And so you can prove from prior postulates the stuff that you made up still makes sense. and corresponds to the prior postulates. Hands if you have a question. Hands if you have a question. If you are going to do something in science, it's always phrased as supporting it, because there's always a possibility of error. We did a whole unit of sig figs last year. We knew it might be wrong. So the only things that might be true are the things that are supported. We also have the possibility that everything you have observed corresponds to a theory and a model that works, but it just works. It might be completely wrong. We just make the assumption that if a model works really, really well, it corresponds to reality. So it's not that it's not true, it's that it works and it might be true, and the other stuff is not true. Yes?
You're contradicting yourself. Like you said that math is made up.
I said math is made up.
Still is chemistry.
I didn't say chemistry is made up.
Well, you said the theories and the law are just rules that people made up.
No, I said a law is a summary. It's just a summary.
That someone created and you believe.
Yeah, we just, no,
It's the same thing as.
I think you're getting confused about the language. The law is just a summary in science. It's not like a legal law. You can still go faster than the speed limit,
You can't go fast enough.
but you can't go faster than the speed of light. And that is a law, because we've just described it as a law. Some things cannot be described as a law because they can't be summarized in a formula.
Wait, how do you know that you can't?
But this has nothing to do with the chemistry. And rapidly, we're running out of time for any demos.
That's totally.
No. Ahem. Chemistry 12 class. I'm expecting people to be paying attention. Relevant questions. Side questions every once in a while are fine. But if everyone is turning around every 5 seconds to talk about something else, you're not going to get through all the material, and I'm still going to test it. We're running out of time. This class is already behind. So I'm trying to get through what we can. I want to show you the demos. They're actually good demos that you can actually see some things coming around. I have one where we can actually see an activated complex, or at least its color, to show that it actually exists. But we can do it all theoretically and just have labs and stuff. But I want to be able to do the other stuff as well. We need to catch up. You can't devolve every 3 seconds. Grade 12, not grade 11. Got it? Okay. Activated complex is a midway molecule in a reaction. And because it's the very tippy top of the curve, if I was to draw this as a curve, say like this particular molecule would exist at the very tippy top. It has the most energy because it has the most bonds. Most bonds. Most energy. At the beginning, they have 2 bonds. And when they collapse, they're going to have 2 bonds. But right now, they have 4 bonds. Because they're double. And so so that is what the activation energy is for. It is weakening the other bonds, but the energy is still there until they snap. And then once it snaps, it's either going to slide down further, in which case it's an exothermic reaction, or it's going to end up higher up, and it's an endothermic reaction. So it is a very high energy. And by high energy, we mean potential energy, unstable substance. They do not exist very long. It's like being at the very tippy top of a tree. Being right here means it either has to slide back and become reactants, or slide forward and become products. Now, I did give you a diagram down below that shows the whole thing as well, so that you have something in addition to yours or my hand drawings. Only thing to discuss, because it's basically a copy, but with this one, this is fruitful, and with this one, it is unfruitful. What is the difference between the two?
Fruitful means the made products, and unfruitful means they revert back to reacting.
That's yes, but if you look at them, why did one make products?
Because the alignment is off, or the
Alignment's off.
direction at which
Yeah. This one has bad geometry. And therefore, that one is unfruitful.
because like they don't, they just return to the, like the product is
Oh, it goes back to what it
yeah, it
was.
goes back to what it was. Fruitful is when it changes. Yeah.
There you go. Okay. Oop. Anybody still writing a couple of words from the last section? Okay. So KBAT B3, we need to define activation energy and get some practice drawing these diagrams, because we're going to draw quite a few free energy diagrams. So first of all, the definition, activation energy is the energy required to form the activated complex. And if we have A2 plus B2 here, I think I'm going to put the other one down below. Let's make it exothermic. Question, Dylan?
Can you please just go up a little bit?
Yep. Now, if these are A2 plus B2 as a generic reaction, we know then we're going to get AB as our product. They're hitting together in similar way to the previous molecules. What would the activated complex look like?
A plus
What would its formula be? A2B2. Because it's everything smushed together.
what are the square brackets for?
Just to show that that's all one thing and we didn't make a mistake because there's a lack of plus. And it's often used to denote the sheer instability of that molecule. It's not a true molecule because it doesn't exist for long enough. The activated complex
Is that supposed to be 2x?
if and only if. Which means you must have these things. Because some things you can say, well, if you have this, but there can be other things that provide it. If with two F's means if and only if. So you only get the activated complex if it hits with the correct geometry. You have sufficient energy to take it up the hill. And that's the energy we define. Under EA. There. Hope that writing was a little neater.
What does EA stand for?
Activation energy. So actually, I'll just make this go there and there then. In the same way that you may use that and that for kinetic and potential energy instead of this and this. And I don't often see activation energy written like that. In physics and chemistry, that actually can stand for something else. A is used way too often in many things. So that tends to be reserved, but I've seen it a couple of times, so it depends on your professor and your textbook. And of course, these are the reactants. And these are the products. And I'm being very pedantic here where I'm labeling the reactants and products each time because this is not a reactant or a product. That's an activated complex and it is neither. It will not stay in that state. It'll either fall back to reactants if it didn't have enough energy or geometry, in which case it wouldn't form at all. Or it'll fall forward and bonds will break and it will become products. But it is literally in between.
Is that only at that one specific moment?
It's only at that particular moment, yeah. As it approaches it, so if we were to go back to this one, this is like right in the middle. These are equally weakened and these are equally forming.
Yeah, what's the arrows?
But if you were like a little further to the left down the thing, then these bonds would be a little stronger and these bonds would be a little weaker. And so that's going up the slide. These would be getting stronger and stronger and stronger as you come back down. But as it hits it, these weaken. And then as it comes down the other side, these just get stronger and stronger and stronger. And those ones? No, other ones. These ones start getting stronger and stronger and stronger, and these start getting weaker and weaker and weaker until finally they snap and the whole thing's lets go. And the amount of energy, as those bonds get weaker and weaker and weaker and the other ones get stronger, is when it's falling in energy. It's getting rid of some bonds. As it is forming extra bonds, that's why the energy is going up, because even though these are getting weaker, they're forming bonds as well. The bonds don't weaken and snap until it gets down to here. Does that make sense? Why do we use reaction coordinate and not time? I've seen it with time before, especially if students write it. Have we explained what reaction coordinate is? Over the course of the reaction.
Did you say reaction progress instead?
You could say progress. Because coordinate implies geometry, so it's like snapshots as they move around. Progress would be absolutely fine. But the reason they don't say time is they don't want to imply that the reaction is not going to happen. Time doesn't mean the reaction is going to happen necessarily. But if you force the reaction to happen, and this is how it progresses, or this is where it is, if you're talking about coordinate, it is just over the course of the reaction. So you're just fixing it. So that's just a, I almost want to say chemistry cultural thing to do. Because if you put time there and you just define that as the time of the reaction, it works. But they don't like that. Feels like it has an error. Anybody still getting that part down? Question?
For the activated complex, it's like on the previous slide, like hydrogen is forming two like half bonds, I guess, with one hydrogen with one iodine.
Yep.
But hydrogen can only form one bond because it has one electron.
Yeah, that's why it's incredibly unstable.
So is the electron just like jumping between the two bonds, or how does that?
Is what?
Like hydrogen only has one electron to form a bond to it.
Bonds aren't strictly speaking the electrons. They're the proton of one atom's attraction to those other electrons. Iodine has lots of electrons. So the attraction that's forming is between the proton of the hydrogen to the iodine. If hydrogen happens to have any electrons, it might be the protons of the iodine having attraction to the hydrogen. But hydrogen only comes with one electron. It originally only had two here. Iodine only had two there. Its attraction is to all of these electrons. So it's not strictly speaking those electrons jumping around. These could snap, and then another electron in the same orbital could be one of the ones that pops out. Also remember, because electrons aren't strictly speaking anywhere. They just have a probability of being somewhere, and they're more of a waveform. So last year when you did quantum chemistry and you learned that a d orbital, well, actually, no, this is a good way to draw for that. A d orbital looks like this. Vaguely remember? And then, of course, p looked like that and s looked like that. But I like using this as an example because that's what it looks like with just one electron in it. And if you take a random sampling, it looks like this the whole time. And so that one electron is sort of smeared out. And it can actually form bonds, theoretically, in 4 places, even though it's just one electron.
Because it moves so fast.
No, because it's not a particle at that point. It's more like a wave.
And waves are everywhere.
Can be, yeah. It's like an energy frequency. Energy frequency is not the right way to say it, but electrons sometimes behave like they're not light. They're definitely a particle in a way, but quantum chemistry with waves works on them. So at that point, I say I didn't do as well in quantum chemistry. It was kind of irritating because it had math like you wouldn't believe. Because all of it is just calculating the probability of an electron being at a spot in a particular time, and then seeing what kind of attraction they're going to form. So the ultimate part is that you don't have to think of it as jumpings around, it'll just form. Okay, describe the changes as in kinetic and potential energy as reactant molecules approach each other. 1252. Now, as electron clouds approach each other, what are they going to exert? They have a charge. What does the charge exert on another charge? Repulsion. So, a repulsive force. You could also talk about the attractive force of the electron to the proton. So the most important word here is that there's a force. Dylan? I'll bring you. As they slow down, what's decreasing, Dylan? What kind of energy?
Molecules slow down.
Kinetic energy or potential energy? If you slow, kinetic, excellent. Well done. And because they're pushing into each other, that's creating a potential for more bonding. That potential energy is going to increase. So this is again referring to this diagram. Our AA bonds and BB bonds are weakening or getting stronger? Weakening. And as they weaken, they would get longer and longening. Lengthening is a good word.
What's the word above it? What's your word?
Sorry?
Blank changes into
Oh. So what is changing into what?
Kinetic into potential.
Kinetic is changing into potential. Or get used to the other notation. Kinetic is changing into potential. Our AB bonds were forming. We're going to draw a little sketch. So we have A. Let's go with B. We already did. They're running into each other. So we have this force. So imply movement with some arrows like we're in a cartoon. And they're bonded to each other in holy matrimony. But this other couple, looking fairly attractive as they press into each other. Now at this point, our A molecules are still bonded, but it's gotten a bit longer. Separate those out a little bit. And they've made some new friends. So, really unstable system. If we're going to get a reaction, which part is it going to break?
Like A and B bonds would break between each other, like AA and B.
Yeah, those ones are going to break there. So the AAB bonds break. And if you break bonds and they snap back, what happens to the potential energy? Decreases. So overall, this was the activated complex. That's a giant X for the end of that, but our AB bonds shorten. And become stronger. And then we get more kinetic energy. Because even if it's endothermic, this process of going up to here for the activation energy, it's still going to drop back down. They still slow down quite a bit, and then they speed up again when they come down. Even if they weren't going as fast as before, even if they're sucking in some energy. Okay. Draw little sketches. What you think the activation energy would look like on that diagram for a slow reaction and a fast reaction. So draw a high activation energy, a low activation energy, and predict if you think it would be slow or fast.
There's so much freckles.
Oh wait, no. It would be decrease your reactions. Activation energy is high, longer for 12
I've had these for like a few weeks and I already should more stuff. People? No. I don't know. They look feel like this. You like
Okay, got it, we got it.
it's like shoot cleaner or whatever, and you just take like a paper towel and you run it around the shoe. Puff it. Yeah, well, that's not the end all. You puff it, and then you take like some shine which is like black. I don't even go to sleep. Rub it really hard with like a brush on the surface, and then you clean it off again.
What the fuck? What the heck? It'll be a surprise. We'll figure it out. And if we hate the food, I'll just make a sandwich. I realized there's like one sandwich I like. Remember that sandwich I packed with me?
All right, come on up. This is 30% hydrogen peroxide. We've actually already seen this reaction. This is a different version of it. Also, as a warning, my version of this tends to be sad. Not as good as you will see on the original. And to make it happen, we add a little bit of. This is just so we can capture the bubbles. Yeah, Element's toothpaste. Yep. But Element's toothpaste, I think Mark Wahlberg is like a whole swimming pool. His looks awesome. My high school teacher mentioned the ceiling with it. Mine is just not to make the expectations as well. When I was teaching grade 9s in 2001, it went perfectly. Same recipe, no idea what it is. The reason it's called, they say toothpaste, is you put a drop of food coloring on either side, and that way it comes out in a particular stripe pattern, like a toothpick sometimes pattern. Okay. There we go. And so, we have that, and then, we had a catalyst. Now, how did you draw your activation energy for a fast reaction? Okay. How about just doing this, and I can't get rid of it. Now, how much would you do it for a slow reaction? Big. And so, a fast reaction, little. What a catalyst does is it takes a big activation energy, and usually by providing the right geometry, it takes it down to a little bit, so it doesn't touch. So hydrogen peroxide is actually reacting really so slowly, you can't even watch the bubbles form. If you wait overnight, they will form very, very slowly. Potassium iodide is another catalyst for this. Where is the same one Europe globally uses? Maybe, or he's secretly using it. You. Coca-Cola. Wow.
Yeah.
Oh, we look at one. Getting a little more. It's not amazing.
Like Mark Roberts will like smell the seed.
Yeah, I am aware that his are so much better than mine.
No, but maybe that's something like maybe that's not really easy to make it. It's like
It's
it's
going. Oh, the iodine will turn brown. You get a lot of foam forming very quickly. It's whiter because you just get bigger bubbles and then you get spread out. There'll always be some brown because that's
actually that's right.
No, they call it that because you get strength happening. It looks like it's not actually too right. You told the story about last week.
Oh no, that's iodine.
Oh, yes, no, fluoride replaced
Fluoride.
yeah,
but not that.
You don't use this, no. You would blow them up.
I'll give you $5 if you do it.
This stuff, you notice where you was, Stratos, this stuff can go wrong fairly quickly. You can't buy 30% hydrogen peroxide in the store for the reason that if you do manage to get it out quickly, you release a lot of oxygen. If there's any fire around at all, of course that would be very good. And it gets very hot very, very quickly. That's something that you will replace quite quickly. But if you're doing the store, cabinet, and obviously it just does that. Oh, and now it's critical. Let's go. Now what's left? What does H2O2, hydrogen peroxide, decompose into? Water. So all that's left is water. This is why it's well, I wouldn't use that iodine as food coloring. Food coloring is fine, but the iodine is not. And if there's any unreacted hydrogen peroxide, that would be very important. And given that it's lab grade, who knows what micro amounts of red other things are doing. If you see candy in the lab, why should you not eat it? No. The cool part is that it's like a few drops in there. But you could go to Thrifties and buy enough cleaning chemicals to fill the whole thing. Instead of one drop, you just need a small bucket.
Like, okay, but like, what is the one drop?
I feel like if you want to know that, you should.
No, but that's like.
If I tell you, that's just cheating.
I feel like then you get bothered by like the FBI hit list.
But we actually have our Mrs. Stewart has to go through investigation whenever she orders something like that's in court. That's what's used in the state. We actually do have to go through that because someone can't just say there are schools that order toxic chemicals. But chemicals are used for everything. There was a campaign a few years ago in which a person who called herself the food or something. She was telling everybody how poisonous Subway sandwiches were because they used a chemical that was used to make chip bars. And it was true. It's used to make chip bars. Just like water is also used to make chip bars. There's nothing particularly toxic about the chemical. But she successfully got Subway to change the formula. So they're now using a new chemical to make the bubbles in the bread. One that is actually slightly less well studied and known. But still using. You wouldn't buy it though. Capitalism rules everything. Back inside.
You just called him a commie for saying capitalism is.
He said wins everything. I mean,
He's
capitalist.
anti-capitalist.
Anti-capitalist.
Anti-capitalism is like low-key good though, because then you can get like proper healthcare and social programs. Yeah, social.
One way money has to be who's fixing the dad?
They all suck.
Money. Not about to get to.
Never been shown in its purest form. It's always corrupted.
So is capitalism though. It's just that corrupt capitalism happens to be not as bad as corrupt communism.
And it's more interesting. Well, it's better hidden as well. Because yeah.
No, corrupt communism is pretty well hidden from people who are under its influence.
Okay, sure. But I'm talking about like yeah, right now look at the US, right? This is all starting with like anti war, right?
Jordan is so boring. Just like this is the song.
Anyways, enough about political.
Oh, I get it.
No, my political hero is Theodore Kaczynski. Alright. The GOAT. When he died, I was like, oh my god, no way. The GOAT is dead. He like, it was like last month thing?
Okay.
Oh no, it was like months ago. It was like June or something.
We still have 2 minutes.
Or earlier.
Let's go, go, go.
My favorite environmental activist slash influencer is Theodore Kaczynski. The vegan teacher. She lives in my neighborhood.
What?
The vegan teacher lives in my neighborhood, and my dad like plays gigs in like pubs and bars and stuff, and she shows up to them. I've seen her.
Ahem.
What did you say to her?
Dylan, I just said ahem. That's the universal sign. Back to attention notes out. Let's go.
That later.
I'm not gonna talk to you about anything. I want to hear about it.
Dylan. So, high EA, slow rate of reaction, low EA, fast rate of reaction. That's PLO B4. B4. Ways to increase the frequency of collisions. How do you make collisions happen faster and more often? Catalyst is a great one because it's the one that isn't. So catalyst doesn't work by increasing collisions. So I'm going to put that like this because I actually discussed it separately. Concentration. Temperature would be one.
Pressure.
Concentration technically isn't. because you're just providing more molecules. So you haven't increased the frequency. You've just provided more.
Temperature.
So temperature definitely would.
Pressure.
And pressure would. Because you still have the same amount. Nice. Enjoy your